Welcome to the video lecture 9 on the topic First Law of Thermodynamics by Professor Prashant S. Shedbalkar, Mechanical Engineering Department, VSM's SRKIT, Nipani. The energy exists in numerous forms such as internal energy. Internal energy means a sensible heat energy. It may be a latent heat energy, chemical energy, nuclear energy. These are the forms of the internal energies, and kinetic energies, potential energy, electrical energy, magnetic energy, and their sum constitutes the total energy E of the system. So total energy, it is indicated by E. E of the system, that is total energy. E indicates the addition of all these forms of energies. So we have written here delta E. Delta E is equals to delta U plus delta kinetic energy plus delta potential energy. So in the absence of electrical and magnetic energies, we have not considered here. So this delta E we can write in this form also, dE equal to, this is nothing but same here, du plus change in kinetic energy. D indicates change in kinetic energy plus change in potential energy. So du is nothing but delta U. We can write this in the form of U2 minus U1. Du change in the internal energy, that is when the system changes from state 1 to state 2. What is the change in internal energy? We are going to write du is nothing but U2 minus U1. Similarly, dKe, that is kinetic energy, or delta Ke, how we are going to write? Kinetic energy formula is 1 upon 2 mv square. This similarly, if the system changes from state 1 to state 2, we are going to write in this form, 1 upon 2 m v2 square minus v1 square. Similarly, for potential energy also, delta P, how we are going to write? P is equals to m into G, Z2 minus Z1. So most system encountered in the practice are stationary. That means there is no change in velocity or elevation. That is kinetic energy and potential energy both are 0. So how we are going to write here in this form? Delta E is equals to delta U when the systems are stationary. Now we are going to define enthalpy. Next, enthalpy, it is denoted by the symbol H. H is equals to U plus PV. That means the sum of internal energy plus product of pressure into volume. It is nothing but the enthalpy. So from the first law of thermodynamics, how we are going to write the equation? Delta Q is equals to du plus delta W. Du, that is nothing but delta E is equals to du. Already just now we have written the equation for the stationary systems, dE plus, so d is replaced by here du. Delta Q is equals to du plus delta W. So if it is integrated over the system, and that is a system is changing from state 1 to state 2, so 1 Q2 equals to du is nothing but U2 minus U1 plus 1 W2. That is work done during the change in state, system changing from state 1 to state 2. So this work done, that is the 1 W2 is equals to integration over 1 is to 2 P into dV. Since we have considered the pressure is constant here, so 1 W2 equal to P, I will take outside, integration of 1 is to 2 dV. Integration of dV will be V. So from 1 to 2 means P into V2 minus V1. So easily I can write, since pressure is constant, that is nothing but P1 is equals to P2. So I have written here P2 V2 minus P1 V1, because pressure is constant, that is P1 is equals to P2 equal to P. We can write here for constant pressure. So now I will substitute this value in this equation. See here, now 1 Q2 is equal to U2 minus U1 plus P2 V2 minus P1 V1. Now I will take this U2 and P2 V2 term one side, and U1 this P1 V1 term one side. So U2 plus P2 V2 minus I will take outside U1 plus P1 V1. I have not altered the equation here. So if I will simplify it, this will be minus U1 only. So this will be minus P1 V1 only. So only minus I have taken outside and I have put these terms in the bracket U1 plus P1 V1. So already we know that we have defined enthalpy is nothing but U plus P into V. So therefore 1 Q2 I can write this as H2 minus H1 because H is equals to U plus PV. Already we know that enthalpy. So here it is U1 plus P1 V1. I can replace it by H1 because H is equals to U plus PV. And for per unit mass means specific enthalpy. If this is denoted divided by M per unit mass, so it is called as the specific enthalpy. It is denoted by small h, that is equals to U plus P into V. It is called as the specific enthalpy. Now, next we will study specific heat. So, specific heat is defined as the quantity or the amount of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius. So how it is a specific heat? Specific heat is symbolically it is represented by capital C. It is equals to delta Q divided by dt into delta M. This delta M means per unit mass. So per unit mass, this delta M is nothing but 1. I can substitute here because it is for a per unit mass. Heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius. So here unit mass means delta M. I will substitute here 1. So this equation becomes C is equals to delta Q divided by delta T. So usually we will be having two specific heats. One is a specific heat at constant pressure and specific heat at constant volume, which are represented by Cp and Cv. Cp means specific heat at constant pressure, where Cv means specific heat at constant volume. So Cp is given by delta Q divided by dt to the P here. P indicates at constant pressure, where Cv is equal to delta Q by dt over the V here. That V indicates constant volume. So now let me write the equation for at constant volume. So as per the first law of thermodynamics, this delta Q is equals to delta E plus W. Delta Q is equals to delta E. I can write in this form also du plus W is nothing but P into dV. Work done. Work done. W is nothing but P into dV. Since this it is a constant volume, that is change in volume will be 0. dV will be equal to 0 because of the constant volume. Then my equation will be delta Q is equals to du only for constant volume. So if we want to write it for per unit mass, so per unit mass means dt, if it is divided by m per unit mass, then it is denoted by small q. Delta Q is equals to du small u for per unit mass dm. So now this delta Q I will replace it by du. So Cv is equals to du divided by dt over constant volume. Here it should be V here, du by dt V. It should be V here, not P. Cv is equals to du divided by dt for constant volume. Now we will write the equation for constant pressure. We know that H is equals to U plus PV enthalpy. So by differentiating this equation, I will get dH is equals to du plus, this is U into V form, that is P into dV plus V into dP. If I will differentiate this term, this will be P into dV plus V into dP. So as it is a constant pressure process, this change in pressure will be 0 because it is a constant pressure process. There will be no change in pressure here. So this term becomes 0 because of the constant pressure. So now my final expression becomes dH is equals to du plus P into dV. So this du plus P into dV, I can replace it by delta Q because as per the first law of thermodynamics, we know that delta Q is equals to du plus P into dV. So therefore dH is equals to delta Q. So again, if we want to write this equation for per unit mass, so then this if this is indicated by small h, dH is equals to, this is also it is denoted by small q delta Q. This equation we have written on the basis per unit mass. So therefore Cp is equals to delta Q by dt. So delta Q I will replace it by dH. So dH divided by dt over the constant pressure. P. Now let us write the equation or relation between specific heat at constant pressure and specific heat at constant volume. So already we know that H is equals to U plus PV. So specific enthalpy, that is per unit mass, small h is equals to small u plus P into V. So H is equals to U plus, we already know the equation, perfect gas equation, that is PV is equals to RT. So PV is replaced by here RT. H is equals to U plus R into T. Now differentiating this above equation. So dH is equals to du plus R into dt, because R is constant here. So differentiation of T will be dt. So this will be du here. Now dH is nothing but Cp into dt. Cp into dt. dH is nothing but Cp into dt here. So dH is replaced by Cp into dt. Similarly, du is replaced by Cv into dt. Already we have proved this, Cv into dt plus R into dt as it is. So in all the equations dt is there. If I will divide this entire equation by dt, so I am going to get the equation Cp is equals to Cv plus R. Therefore, Cp minus Cv is equals to R. So this is the relation between specific heat at constant pressure and the specific heat at constant volume is equals to R, that is universal gas constant.